So I know that your problems in this week's module jump around a bit, and you're using different definitions of trigonometric functions. So I wanted to create a video with an overview of 3 different ways that we look at the definition of trigonometric functions over the next few weeks. I wanted to start with the definition that might be most familiar to you, or if you remember any trigonometry from, say, high school, it's likely to be right triangle trigonometry. If you remember the acronym SOHCAHTOA, that's referring, and this should be an A, SOHCAHTOA, that's referring to the right triangle definitions of the trig functions. So first thing, a naming convention, when we talk about triangle ABC, say in homework problems or exam problems, in triangle ABC, C is always going to be your right angle. So in my picture right here, C would be this angle here. Your other 2 angles are A and B, and it doesn't really matter which one's which when you set this up. But the important thing is the convention is to use capital letters for the angles and then lowercase letters for the sides. And we name the opposite side with the lowercase of each letter. So if this is angle A right here, then this will be side A. That's opposite of angle A. And then if this is angle B right here, then this will be side B, opposite of angle B. And then since C will always be the right angle, the 90-degree angle, then side C is always going to be the one that's opposite, which has a special name. The side that's opposite of the 90-degree angle is called the hypotenuse. This is a T right here. All right, so one way to define the trigonometric functions of either A or B. Let's go with A, because that's what I have in the picture below. According to the lengths of the sides of this triangle. So notice that, so lowercase a here is the side that's opposite of angle A. And then B is, we call it the adjacent side. So it's the side that's touching A, the angle A, that is not the hypotenuse. And then, as I said up above, the hypotenuse is always the angle that's opposite of the 90-degree angle. Now, what you call opposite side and what you call adjacent side, that's relative to A. If we're defining trig functions of A, so say sine of A and cosine of A, then what we call opposite side and what we call adjacent is, again, it's relative to the angle that we're looking at. So in this case, angle A. So let me tie it back to this acronym here. So sine is, the O and the H stand for opposite over hypotenuse. And I'm just going to do shorthand right here. So in this case, that would be opposite side is A over C. Cosine is, so that's the AH, CAH part of this. So cosine is adjacent over hypotenuse. And then tangent, that's the TOA, opposite over adjacent. Again, I'm going to do shorthand. Okay, and let me scroll down here just to show you. And I have a PDF with these definitions posted with this with the video link to this video. So anyway, this is what I just wrote up above. Sine is opposite over hypotenuse. That's the so part of SOHCAHTOA. Sine's opposite over hypotenuse. Cosine is adjacent over hypotenuse. That's the ca part. Tangent's opposite over adjacent. And then notice you have these 3 other trig functions. So there's actually a total of 6 basic trigonometric functions. We've got cotangent, secant, and cosecant. But notice something else. So if you compare tangent with cotangent, cotangent is adjacent over opposite. So it's the reciprocal of tangent. And then if you compare cosine and secant, notice secant's hypotenuse over adjacent, so it's just the reciprocal of cosine. And then cosecant's hypotenuse over opposite, so it's just the reciprocal of sine. And I have those reciprocal relationships in this chart here, which is also on your PDF there. So that's that. We come up with that just by noting that, well, hey, this ratio is the reciprocal of this ratio. So that's where those reciprocal relationships come from. Okay, now a couple of things. If I wanted to write down, let's say, cosine of angle B, then just a quick heads up that, all right, so side B down up here is the opposite side. This is opposite of B, and so we would call side A in this scenario the side that's adjacent to B. So if cosine is, so that's the co part, adjacent over opposite, co parts, adjacent over hypotenuse, but it's cosine of B, then I want the adjacent side to B, which is side A, over hypotenuse, which is always going to be C. But I just want to point out that make sure that when you're defining adjacent side and opposite side, that's relative to whatever angle you have inside your trig function. Okay, one other thing about this. So this definition is great. The major limitation is that this is only going to work if your angle A is between 0 and 90 degrees. If it's a negative angle or if it's bigger than 90 degrees, then we can't really set up the triangle the way we have here. And so this whole right triangle definition really only works for acute angles between 0 and 90 degrees. A lot of your homework, by the way, is going to deal with this right triangle definition of the trig functions. So I'm scrolling down to this definition number 2, which allows us to extend the definition of the trig functions to something that works for angles that are not between 0 and 90 degrees. And I'm just having a hard time changing to a pen. I'll just have to write in green. That's fine. Okay, so look, this looks very similar actually to what we had up above. And I'm going to redraw this just to kind of explain where this is coming from. So imagine you've got this angle theta, and we're drawing it for now as something between 0 and 90 degrees, because I want to set this up so it coincides with the definition we have up above for part 1. Choose this point xy as any point along the terminal side. So that's where that xy is coming from. Xy is any point on the terminal side of theta, and r is the distance from the origin to that point xy. So if you use the distance formula, which you guys might remember is, so it's the change in x squared, so it's x2 minus x1 squared plus y2 minus y1 squared. Or, I'll write that down. But maybe we could use the picture to figure out something better. So say you drop a line straight down. Then this vertical distance right here is your y-coordinate, right? And this horizontal distance right here is your x-coordinate. And then there's, I know I've just redrawn the picture that's over here. But now you could think about this. So this is going to be a right angle right here. Because this is vertical, this is horizontal. So now we can think of it in terms of good old SOHCAHTOA, the right triangle definition. And so, well, let's see, if we're talking relative to this angle theta, then sine is opposite, which is y, over hypotenuse, r. So that's what I have here. Cosine would be adjacent, which is x, over hypotenuse, which is r. And then tangent would be opposite, y over x. Okay, and then your reciprocals. Now, I kind of trailed off over here. I started to explain where this r, where we're going to get the value of r. So if it's the distance from 0, 0 to xy, well, kind of using this picture, we could see r is the hypotenuse. So according to the Pythagorean theorem, x squared plus y squared is equal to r squared. And we're always taking r as the distance from the origin to that point. So it's always going to be the positive root of x squared plus y squared. And actually both of these equations might come in handy at points in your homework. But just don't forget that r is always going to be positive. I wish I would have said always positive, but you get my point. Okay, so this is your XYR definition, and you'll be using this, yeah, and here, let me write that down, because that's the way I refer to it. You'll use this definition a lot more next week. But if I scroll down again to the unit circle definition, okay, so the idea down here is that, okay, we choose a point on the terminal side. It's just like that XYR definition up above, but suppose we make the radius always 1. That's what the unit circle is. It's a circle centered at the origin with radius 1. So all of these distances right here, all of the r values are 1. And so notice that in these definitions here, all I did was I took the XYR definitions above, yeah, and actually now I can get them both on the screen, but I just changed all the r's to 1. So if you are using a point that's on a unit circle, meaning if you are certain that r is equal to 1, then sine of theta is just y, because it'd be y over 1. And cosine of theta is just x, whatever the x coordinate is for your point that lies on the terminal side and where it intersects with the unit circle. So I pasted a little unit circle down here. Let me see if I can pan down. And maybe even make this bigger. Let's see. I think I can. Yes. Okay. Then if you wanted to find something like sine of pi over 6 radians, you would just locate pi over 6 radians, find the corresponding xy coordinates, and sine is defined as y over r, so that's going to be 1/2 over 1. So sine is just the y coordinate. Let me do a couple more of these. So if we wanted to find, let's say, cosine of 5 pi over 3, so you would locate 5 pi over 3 radians, that's right here. Your corresponding point on the unit circle is this right here. And cosine is defined as x over r, but radius is 1, so just x, which is 1/2 again. I didn't mean for that to happen. I didn't think that through. But that's the idea. I have another video where I thoroughly go through finding values of trig functions from the unit circle, but mainly I wanted to give you guys the overview of these different definitions of trig functions, and they do all coincide. So if you have an angle between 0 and 90 degrees, you can think of it as SOHCAHTOA. It's the sides of a right triangle. If you have an angle that's either negative or bigger than 90 degrees, then you think of it this way, which is, let me draw the whole xy plane. Let's say your angle is this one. So that's much bigger than 90 degrees. You choose any point on the terminal side. You have these coordinates x, y. You have this distance from the origin out to this point. We call that r. And then you can define the trig functions this way. And it turns out that that completely coincides with our definition with the right triangle. If it happens to be between 0 and 90 degrees, it's going to line right up with what we said previously. But this now works for negative angles, for really big angles, for really small angles. This way you can find a trig function of any angle. And then the last one, just think of it as it's this XYR definition, but we're trying to make things a bit more convenient. So we think of a circle with radius 1. If the radius is always 1, then sine's just going to equal y, cosine's just going to equal x, and so on.